Welcome to the deep dive. Today we are strapping into a modified Avro Lancaster, feeling the vibration of 4 Merlin engines as we skim the water at precisely 60 feet.
Yeah, it's quite a ride we're taking.
This isn't just a military history lesson, it's a deep dive into an improbable technological mission operation Chastise, and the engineering genius that turned a skipped bomb into a weapon of strategic destruction.
It really is an amazing story. It's where, theoretical physics meets the ultimate field test, all crammed into one single incredibly high-stakes night in 1943.
Right.
And what often gets overlooked, I think, is the sheer ingenuity involved.
Yeah.
Relics of the training, the practice runs, they still turn up today.
Yeah.
Connects that moment right back to us.
That's actually the perfect place to kick this off. Because in the summer of 2018, something pretty surprising was found, connecting directly to this mission.
Oh, yeah. What was that?
A British father and son, they were just out catching crabs along Reculver Beach in Kent, which turns out was an area the RAF used for testing. And they stumbled upon something really dense in the mud. A cylindrical concrete core.
Yes. A dummy bomb. Basically a practice weight.
Exactly.
Those were used to train the crews, getting the feel for loading, handling, even dropping the weapon codenamed Upkeep, long before they ever got near a live explosive.
So that piece of concrete, it really represents hundreds of hours of painstaking practice.
Absolutely. Grueling, dangerous practice at that.
Good. So let's unpack this mission. Our goal today, for you listening, is to really get under the skin of how the British RAF took their workhorse bomber, the Avro Lancaster, and completely re-engineered it, all to deliver this, frankly bizarre, backspinning, bouncing bomb. We want you to grasp the absolute convergence of engineering brilliance, air power logistics, and the almost unbelievable precision needed to pull it off.
It's that combination that's key.
Yeah. This deep dive should leave you with a real understanding of why this raid is still considered one of World War II's great technological achievements.
And, to really get the solution, you have to first understand the problem that they were facing. It was a massive strategic challenge for the British in the early 40s.
Absolutely. So let's dive into that strategic problem and the, frankly, elegant solution that Barnes Wallis came up with.
Right. So long before the war really hit its stride, British planners were already looking at ways to, cripple Germany's industrial heartland.
Makes sense. Target the engine room.
Exactly. And their focus pretty quickly zeroed in on the Ruhr region dams. The Möhne, the Eder, the Sorp, these massive structures.
Why the dams specifically? Power generation.
That was part of it, sure. But the main goal, the really big prize, was catastrophic flooding. If you could breach those dams, the resulting floodwater wouldn't just knock out power. It would devastate factories, mines, transport infrastructure.
Yeah.
Basically halted a huge chunk of the German war machine that relied on the Ruhr Valley.
So a knockout blow, potentially. But surely conventional bombing could take out a dam.
You'd think so, but no. These dams were just enormous feats of engineering, built to withstand incredible pressure. Standard bombs dropped from high altitude, they just weren't doing significant damage.
So that's where Barnes Wallis comes in. He was an aircraft designer at Vickers, right? Already known for the Wellington bomber.
That's him, a brilliant engineer. And by 1941, he was apparently obsessed with his dam problem. He looked at it differently.
How so?
Wallis figured out that the real key wasn't hitting the top of the dam, but delivering a massive shock wave underwater, right up against the interface of the dam wall.
So using the water itself to transmit the force.
Precisely. His calculations showed that a large bomb detonating underwater close to the base would create this concentrated pressure wave, a shock wave, that would do far more structural damage than any impact on the surface. It's about internal pressure, not just kinetic energy from above.
That's a critical insight. It completely changes the attack profile, doesn't it? From high-altitude bombing to some kind of specialized underwater attack. But hang on, if you need an underwater explosion, why not just use standard naval torpedoes?
The Germans had thought of that. They weren't taking any chances. They'd installed these heavy steel anti-torpedo nets, submerged just below the surface in the reservoirs.
Okay, so any torpedo dropped conventionally would just get tangled up.
Exactly. Caught in the nets before it could ever reach the dam wall. Made a standard underwater attack pretty much impossible.
And this is where the genius comes in. The aha moment for Wallis.
This is it. Wallis realized, probably inspired by skipping stones, that if you could drop a specifically shaped bomb with significant backspin, it would actually skip across the water's surface.
Like a skimming stone, bouncing right over the nets.
Precisely. It sounds almost playful, but the physics is solid. It relies on the Magnus effect, the same reason a spinning ball curves in the air. The backspin gives it lift and stability as it skips.
But it wasn't just about clearing the nets, was it? The backspin had another crucial role.
That's right. Scale model tests showed something vital. When the cylindrical bomb, still spinning backwards, finally hit the smooth dam face, that backspin would cause it to sort of roll down the wall.
Oh, I see. So it hugs the dam face as it sinks.
Exactly, ensuring it stayed right up against the wall until it reached the perfect detonation depth. Without the backskin, it might drift away as it sank, lessening the shockwave's impact.
Incredible. So this thinking led directly to the design of the weapon itself, the upkeep bomb. It had to be huge, but also specifically designed for this skipping and sinking process.
Absolutely huge. It was this massive cylinder, air-dropped, of course. Dimensions were 60 inches long, 50 inches in diameter. Just the sheer size meant it couldn't fit inside a standard bomb bay.
Fit, wow. And the weight.
Staggering, 9,250 pounds in total, nearly 5 tons.
And packed inside that, what was the actual explosive payload?
Okay, so out of that 9,250 pounds, a whopping 6,600 pounds was Torpex.
Corpex. I know TNT, but Torpex.
Yeah, Torpex was a significantly more powerful explosive, about 50% more punch by weight than TNT. It was ideal for generating that maximum underwater shockwave Wallis needed.
And this explosive charge was just packed into the cylinder.
It was wrapped in a protective steel casing, about 3/8 of an inch thick, enough to keep it intact during the drop and skip.
Right. Now, the detonation, how did they ensure it exploded at exactly the right depth?
That was critical. They used 3 Mark IV hydrostatic pistols. These are basically pressure-sensitive fuses.
Okay.
They were very precisely calibrated to trigger the main charge, only when the bomb reached a depth of exactly 30 feet.
30 feet, not 25, not 35, exactly 30. Why that specific depth?
Wallis's calculations again. That 30-foot depth was determined to be the sweet spot, the optimal depth to transmit the maximum shockwave force against the dam's base before the pressure started dissipating too much into the surrounding water.
Precision engineering right down to the fuse. Now, obviously, this was top secret tech. What if a bomb didn't go off or was dropped unexploded? They couldn't risk the Germans getting their hands on it.
No, absolutely not. So they built in a safety measure, a self-destruct pistol.
How did that work?
It was designed to trigger automatically after a set time delay if the primary hydrostatic fuses failed. The idea was to destroy the bomb completely, preventing the Germans from reverse engineering it.
A vital insurance policy, though, as we'll see, it wasn't always foolproof.
Unfortunately not, but the intention was there. So, okay, now we've got this incredible, highly specialized weapon.
Yep, the upkeep bomb.
Now you need an aircraft capable of carrying it and, just as importantly, delivering it under these insane conditions. You needed more than just a heavy lifter. You needed something adaptable, something that could handle extreme low-level flight and major modifications.
Enter the Avro Lancaster, the Mark I specifically.
The Lanc. Yeah, the absolute backbone of RAF Bomber Command. It had only been introduced in February 1942, so it was still relatively new, but already proving itself.
Crewed by 7 airmen, right, and known for being reliable.
Very reliable. And crucially, it had this huge, long, unobstructed bomb bay. That was key.
And powered by
4 Rolls-Royce Merlin XX engines. Liquid-cooled V12s, about 1,280 horsepower each, gave it a decent cruise speed, around 200 miles per hour, and the range needed to get deep into Germany, like the Ruhr Valley and back.
But the big advantage was that payload capacity.
Definitely. The standard Lanc could carry 14,000 pounds of bombs. That huge capacity gave them the margin they needed to handle the 9,250-pound upkeep, plus all the extra gear needed for the spin mechanism.
Okay, let's put that into context for listeners. How did the Lancaster stack up against the main American heavy bombers at the time? Say, the B-17 Flying Fortress or the B-24 Liberator?
Good comparison. Payload-wise, the Lancaster had a clear edge. It could haul more bombs further than either the B-17 or the B-24. Made it perfect for the RAF's strategy of heavy night bombing.
But there was a trade-off, wasn't there? Something about altitude.
A massive trade-off in standard bombing doctrine, yes. The service ceiling.
How high could they fly?
The Lancaster topped out around 21,400 feet, which sounds high, but...
But the American bombers...
The B-17G could get up to, what, 35,600 feet?
Yeah.
And the B-24J could reach 28,000 feet. That extra altitude was a huge advantage for daylight bombing, putting them above a lot of the German flak and making fighter interception harder.
So the Lancaster was more vulnerable in that sense?
In typical high-altitude raids, yes. But for Operation Chastise, that lower ceiling was completely irrelevant. Actually, maybe even a benefit in some ways.
How so?
Because this mission demanded the exact opposite of high altitude. It needed stable, predictable handling at extremely low levels, 60 feet. The Lancaster's robust, relatively simple design proved very adaptable for the radical modifications they needed to make.
And radical feels like the right word. These modified planes were designated Type 464 provisioning. It sounds like major surgery was required.
It really was. Open-heart surgery for an aircraft. First off, that giant upkeep bomb simply wouldn't fit inside, as we said. So the bomb bay doors, gone, completely removed.
And the bomb just hung underneath.
Exactly. They installed these heavy V-shaped caliper arms under the fuselage. These arms essentially cradled the cylindrical bomb, holding it tethered to the belly of the plane.
Okay, holding it is one thing. But what about the spin? That crucial 500 RPM backspin. How on earth did they impart that to a nearly 5-ton bomb hanging under the plane just before dropping it?
This was maybe the trickiest bit of engineering. They used a Vickers variable speed hydraulic gear system.
Okay.
Imagine a powerful hydraulic motor mounted inside the modified bomb bay structure. This motor drove a wide, heavy belt that looped around the circumference of the upkeep bomb.
Like a giant fan belt.
Sort of, yeah, but incredibly strong. In the final seconds of the attack run, this hydraulic system had to spool up that massive bomb, spinning it backwards at precisely 500 revolutions per minute.
Wow. The vibration, the gyroscopic forces, the stress on the airframe, especially flying at only 60 feet. That must have been intense.
Immense. And remember, this wasn't off-the-shelf tech. This was custom-built, bespoke engineering. It had to work perfectly, first time, during the actual attack. No second chances.
All that extra machinery added weight and complexity, presumably.
It did. And since every ounce mattered for low-level performance and stability, they stripped the Lancasters down where they could. The mid-upper gun turret, for example, completely removed.
You just took it out.
Yep. Covered the hole with a simple aerodynamic fairing to reduce weight and drag. Every little bit helped.
There's also a detail in the sources about the engines on these specific Type 464s. They weren't the standard British Merlins.
That's right. They were actually swapped out for American-built Packard Merlin 28 engines, licensed versions of the Rolls-Royce engine.
Any particular reason? Performance difference.
Probably more down to logistics and availability. Production schedules were incredibly tight. The RAF ordered 21 of these modified Lancasters, and they were racing against the clock to get them ready for the mission window in spring '43.
Which brings us neatly to perhaps the biggest challenge of all. Not the bomb, not the plane modifications, but the act of delivering it. The precision problem.
This is where it gets almost unbelievably difficult. Precision was absolutely everything.
Because Wallis's physics dictated very specific release parameters.
Exactly. All the testing, all the calculations showed the bomb had to be released at a very specific ground speed, and more critically, a very specific height above the water.
Get it wrong, and
Too high, the bomb skips too far, maybe bounces right over the dam entirely. Too low, it hits the water too hard, sinks immediately, doesn't skip, doesn't reach the wall. Useless.
And those magic numbers were?
Exactly 60 feet altitude off the water surface while flying at precisely 220 miles per hour.
60 feet. I keep coming back to that. It's roughly the height of a 4-story building. Flying that low, at speed, over water, at night. It's mind-boggling.
And here's the kicker. No standard RAF altimeter at the time was anywhere near accurate enough to reliably measure 60 feet over a potentially choppy water surface. A small wave could throw off a pressure altimeter completely.
So how do they solve it? They needed a foolproof way to know their exact height.
They needed something visual, something immediate. And the solution they came up with is pure low-tech genius. It's the stuff of legend. The Aldous spotlights.
Ah, yes. Tell us about those.
Okay, so they took 2 standard Aldous signal lamps, the kind used for signaling between ships or aircraft. They mounted these rigidly onto the aircraft.
Right, exactly.
One was fixed in the nose, pointing downwards and slightly forwards, casting a circle of light on the water ahead. The second one was mounted underneath the fuselage, further back, behind where the bomb bay used to be, also casting a circle of light downwards.
2 spotlights. Okay, what's the trick?
The geometric genius was in the angling. They were angled inwards with absolute precision. The geometry was worked out so that only when the aircraft was exactly 60 feet above the water would the 2 circles of light projected onto the surface converge and merge into a perfect figure-8 shape.
A figure 8, visible to the pilot or bombardier.
Visible on the water surface, just ahead of the starboard wing, typically watched by the navigator or bombardier. The moment those 2 circles touched and formed a clear figure 8, they knew. Bang. 60 feet.
That's incredible. So simple, so visual, no complex instruments to fail, just basic geometry.
Exactly. An immediate, unmistakable cue. But altitude was only half the battle. They still needed to release the bomb at the perfect distance from the dam wall for the skips to work out.
Right. How did they judge that? Standard bomb sights wouldn't work for this kind of low-level specific distance drop, would they?
No, completely useless. So again, they needed a low-tech, bespoke solution, and this one came from Wing Commander Charles Dan.
What did he devise?
It sounds almost comical, but it was deadly serious and effective. He constructed a simple handheld sighting device, literally a triangular piece of wood.
A piece of wood?
Yeah, with a small peephole at the top corner, the apex.
Yeah.
And then, along the base of the triangle, he hammered in 2 small nails at very specific points.
Okay. A wooden triangle with a peephole and 2 nails. How did that help?
The bombardier would look through the peephole. The dams, like Moan and Eder, had distinctive towers at each end, sluice towers or valve towers. The bombardier's job was to line up the 2 nails in his wooden sight so they visually bracketed or perfectly aligned with those 2 towers on the actual dam.
So when the apparent distance between the nails matched the apparent distance between the dam towers.
It meant the aircraft was at the exact predetermined distance from the dam face for the correct release point. Simple trigonometry executed with a piece of wood.
It's just remarkable, isn't it? One of the most advanced high-stakes raids of the war, relying on spotlights forming a figure 8 and a wooden sight with nails.
It really underscores the unique challenge. There just wasn't any existing technology for this kind of pinpoint, ultra-low-level attack. They had to invent it, often using very basic principles.
So you've got the plane, you've got the bomb, you've got these ingenious aiming devices. Who flies them? Who takes on this mission?
For that, they formed a brand new specialist squadron. No, 617 Squadron. And command was given to a highly experienced, highly decorated bomber pilot, Wing Commander Guy Gibson, a veteran even then.
And the training for 617 Squadron must have been intense.
Intense doesn't even cover it. By all accounts, it was absolutely brutal and incredibly dangerous, focused entirely on low-level night flying, often over water, skimming just above the waves or tree lines.
They basically threw out the rule book.
Completely. Standard RAF flying regulations were suspended for them. They were practicing flying at speeds and heights that would normally court disaster, flying under power lines, navigating by moonlight through valleys, things that defied standard procedure and, frankly, instinct.
You can only imagine the psychological pressure. Holding 60 feet over black water at 220 mph night after night, knowing a tiny mistake means instantly hitting the water.
They're literally learning to fly in a way that went against every survival instinct.
Yeah.
And they discovered new dangers along the way.
Such as?
During practice drops with inert bombs at the Reculver test range, they found out the sheer force of the water displaced by the bomb hitting the surface, splashback, the plume could actually damage the tail of the aircraft if they flew straight over it.
So the bomb itself could bring them down?
Potentially, yeah. The water plume was huge, so they had to incorporate another dangerous maneuver, pulling up hard and fast immediately after releasing the bomb to clear the splash, just adding another layer of complexity to an already critical few seconds.
Were there other equipment changes they made besides the bomb gear and sights?
Yeah, a couple of key ones for low-level work. Standard radios often struggle close to the ground due to line-of-sight issues and interference, so they swapped those out for very high-frequency VHF sets, which were generally more reliable at low altitude.
Makes sense. Anything else?
Gibson made a specific call about ammunition for the Lancaster's defensive guns.
What was that?
They loaded them only with tracer rounds, highly visible tracer rounds.
Wait, wouldn't that just make them more visible to German flak gunners on the dams, giving away their exact position?
That was the risk, absolutely. But Gibson's thinking, or the thinking behind it, was psychological.
How so?
The hope was that the bright streams of tracer fire pouring towards the flak positions would be so intimidating, so visually overwhelming, that it would force the German gunners to keep their heads down, disrupting their aim during those critical final seconds of the approach.
So it was a gamble trading better concealment for potentially better suppression through sheer visual shock.
Exactly. A calculated risk to buy those vital seconds needed to line up the shot.
Okay, so training's complete, planes are modified, crews are as ready as they'll ever be. But there was still a moment of sheer terror just before the mission launched.
Yes. Just 2 days before the raid was scheduled, they conducted the first and only test drop using a fully live upkeep bomb. Imagine the pressure on that crew, knowing the entire operation hinged on this single test.
And did it work?
It did, thankfully. But the sources also mention another near disaster around the same time. One of the live bombs was accidentally dropped during loading onto a Lancaster at their base, RAF Scampton.
Oh my God, it fell onto the tarmac.
It fell right to the ground.
Yeah.
Miraculously, the impact wasn't hard enough or at the right angle to trigger those sensitive hydrostatic pistols. If it had gone off, It would have been catastrophic right there on the airfield.
A disaster narrowly averted. Talk about pressure. And the timing for the actual raid, that wasn't random either, was it? It was dictated by the calendar.
Very specifically, the window was May 14th to 16th, 1943. Why then? Because that's when the reservoirs behind the dams would be at their absolute fullest after the spring snowmelt and rains.
Maximum water pressure, maximum potential flood damage if breached.
Exactly. Maximize the impact. The final go-ahead was given by the RAF for the night of May 16th.
Now, before they took off, the crews needed to be crystal clear on something important. The targets weren't all the same. The bouncing bomb technique wasn't suitable for all the dams.
Crucial point. They were briefed on attacking two fundamentally different types of dam construction, requiring two different attack methods.
Okay, what were the types?
First, you had the gravity dams. These were the big ones. Moan, Eater, and also the secondary targets like Lister, Ennepe, Daimel. Massive structures of concrete and masonry, held in place primarily by their own immense weight.
And for these?
For these gravity dams, the attack run had to be over the reservoir, using the full bouncing bomb technique. Backspin engaged, Aldous lights for height, wooden sight for distance, skip it across the water to hit the interface.
Standard procedure, as it were. What was the second type?
The second type was the earth dam, and the key target here was the Sorp dam. Structurally very different. It was basically a huge embankment of earth and rock fill with sloping sides built around a central concrete core for water tightness.
So bouncing a bomb off a sloping earth bank wouldn't work.
No, not effectively. The bomb would likely dig in or deflect unpredictably. So, for the Sorp, the attack plan was completely different.
How so?
The bomb was to be dropped without any backspin. And the approach wasn't across the reservoir towards the dam face, but flying along the length of the dam crest, dropping the bomb near the top.
Aiming to breach the central core near the top.
Exactly. The idea was the explosion would shatter the core and cause the earthen banks above it to collapse inwards, creating the breach. But this approach, flying low and steady along the dam crest, was arguably even more difficult and dangerous, especially navigating the surrounding terrain in the dark.
Two distinct dam types, two distinct attack profiles, adds another layer of complexity.
It certainly does. So the night of May 16th arrives. The raid is launched in three distinct waves.
Wave 1. Who were they and what was their target?
Wave 1 consisted of 9 aircraft. They departed just after 9:30 p.m. Primary target, Moni Dam first, then, if successful, move on to Etter Dam. This wave included the key leaders, Gibson himself, Hopgood, Martin, the experienced hands.
What happened at the moat? It was defended, right?
Oh yes, heavily defended with flak guns. The scene was apparently terrifying.
Yeah.
Gibson went in first, using the spotlights, using the wooden sight. His bomb bounced perfectly, detonated, but just a bit too far from the wall.
So no breach on the first try.
No breach, but crucially, his bomb did destroy the underwater anti-torpedo nets. It cleared the path.
And Gibson didn't just leave then.
No. This is where his leadership was incredible. He started circling the dam at low level, deliberately drawing the German flak fire towards his own aircraft, trying to give the following planes a clearer run. An astonishingly brave move.
Wow. So who went in next?
Hopgood. But as he came in, his Lancaster was immediately hit hard by flak. Damaged, struggling, she released his bomb, but it was slightly late. It actually skipped over the dam crest.
Over the top.
Yeah. Detonated behind the dam, destroying a power station there,
Yeah.
but obviously doing nothing to the dam itself. And tragically, Hopgood's plane exploded moments later. Though remarkably, 3 of his crew managed to bail out and survive.
Terrible loss. Did the next run fare better?
Martin went in next, but his run was slightly off-center. Bomb didn't breach. Then another pilot, Young, flew a run that seemed to stress the already weakened structure. It wasn't until the 5th aircraft, piloted by David Maltby, came in.
This was the one.
This was it. Maltby lined it up, released perfectly. The bomb skipped, hit the wall, rolled down, sank. Detonation. Gibson, still circling, watched a massive geyser of water erupt.
And the breach?
He saw it happen. A huge chunk of the dam wall seemed to just crumble and vanish. He immediately got on the radio, called off Shannon, who was about to start his run, and confirmed Moni is gone.
Incredible moment. One down. Where did they head next?
Gibson gathered the remaining aircraft from his wave, those that still had their bombs, and led them towards the Etter Dam.
Now, Eater was different, wasn't it? Less defended, but tricky terrain.
Exactly. No flak guns protecting Eater. It was considered too remote, but it was nestled deep in a steep, winding valley. The real defense was the geography.
Meaning the approach was difficult?
Extremely. Pilots had to dive steeply down into the valley, level off at precisely 60 feet, just seconds before the dam wall appeared out of the darkness, all while navigating the hillsides.
Oh.
Unbelievably demanding flying.
Who went in first at Eater?
Shannon tried first, made several runs, but had to abort each time. couldn't get the alignment right in difficult conditions. Then Maudsley went in. But his run ended in disaster. He released the bomb fractionally too late. It hit the very top of the dam wall, the parapet.
Oh, no.
The resulting explosion destroyed his Lancaster instantly.
Oh.
No survivors, a terrible price. That left only one aircraft with a bomb. Last night.
The last chance for Eater?
Knight made one aborted run, then came around again. Lined it up, dropped the bomb, and bounced 3 times, hit the dam slightly off-center, sank, and detonated.
And the result?
Gibson, watching, saw the Eater dam just collapse. His description, apparently radioed back, was vivid, as if a gigantic hand had pushed a hole through cardboard.
Wow, so 2 dams breached by Wave 1, Moni and Ader. A success, but costly.
Very costly. And the losses weren't over. On the return flight, Pilot Officer Young's aircraft was shot down over the Dutch coast.
Meanwhile, Wave 2 was in the air. What was their objective?
Wave 2 comprised 5 aircraft. Their primary target was the Sorp Dam, that difficult earth dam requiring the different tack profile. And their routes took them over heavily defended areas like near the Frisian Islands.
Did they fare any better?
No. Wave 2 ran into immediate and devastating trouble. The first aircraft, flown by Flight Sergeant Barlow, reached Germany, but then simply vanished without trace. Radio silence. Assumed shot down.
Just disappeared. But there was a grim consequence to that loss, wasn't there? Something about his bomb.
Yes, this was a huge intelligence failure for the British. Barlow's Lancaster crashed relatively intact, and the Germans recovered his upkeep bomb.
This secret weapon.
And for reasons that are still debated, maybe an oversight, maybe a specific decision for that aircraft, this particular bomb was not fitted with the self-destruct mechanism.
You're kidding. They recovered a live, intact upkeep.
They did. An absolute intelligence catastrophe. The Germans now had the Allies' revolutionary secret weapon to study, a massive own goal hidden within the mission's success.
Unbelievable. What about the rest of Wave 2?
It went badly. Monroe's aircraft was hit by flak, lost hydraulics and communications, had to limp back to base. Byers was shot down near Texel. Rice, the pilot, misjudged his altitude near the coast, actually hit the water surface.
Hit the water?
Momentarily. Hard enough to tear the upkeep bomb clean off the aircraft. He had no weapon left, so he had to abort and return too.
So out of 5 aircraft, only 1 made it to the Sorp target.
Just one, Joe McCarthy. And he had terrible luck. His assigned aircraft had mechanical problems, so he was flying the squadron's spare Lancaster.
What was wrong with the spare?
Crucially, it hadn't been fitted with the special Aldous spotlights for precise altitude control.
No spotlights. How could he possibly judge 60 feet over the Sorp reservoir in the dark?
He couldn't, not accurately. He was flying blind on altitude, trying to execute that incredibly difficult, long, straight run along the Earth Dam's crest. He had to rely purely on instinct and visual cues from the surrounding landscape.
How many attempts did he make?
Agonizingly, he made 10 separate runs over the Sorp, trying to get the height and line right in the fog and darkness before finally feeling confident enough to drop his bomb without spin, as per the briefing for Sorp.
Did it work? Did he breach it?
He saw the explosion cause some crumbling along the crest of the dam. Damage was definitely done. But critically, no breach. The Sorp Dam held. Structurally, it was still intact after McCarthy's attack.
So Wave 2. Heavy losses, an intelligence disaster with a recovered bomb, and no breach at Sorp. What about Wave 3?
Wave 3 was the reserve force, 5 more aircraft. They actually took off much later, around midnight, and flew out awaiting radio instructions based on the result of the first 2 waves.
So they were targeted dynamically?
Yes. But by the time they were receiving targets, dawn was approaching, and German defenses were fully alerted. They flew into a hornet's nest.
Losses.
Immediate and heavy. Otley's aircraft was shot down by flak shortly after receiving instructions. Burpee's aircraft met the same fate soon after. 2 lost almost straight away.
Who was left? Where were they sent?
Pilot Officer Ken Brown was directed to try the Sorp again, to see if he could finish the job McCarthy started.
Did he have the spotlights?
Unclear from the main sources if his specific aircraft did, but the conditions were terrible mist, increasing daylight. He made numerous runs, struggling with visibility and the tricky approach, before finally dropping his bomb near the center of the dam crest.
Any more success than McCarthy?
He circled back and observed the damage. His bomb caused more significant crumbling along the top than McCarthy's had, breaking up the crest further. But still, no catastrophic breach. The Sorp Dam, though damaged, remained standing.
What about the other Wave 3 aircraft?
One pilot, William Townsend, was tasked with hitting the Menipee Dam. But in the poor visibility and confusion, he mistakenly attacked the nearby Bever Dam instead. Dropped his bomb. It caused no significant damage to the wrong target.
Attacked the wrong dam. Oh, dear.
Yeah, fog of war, literally. And the final aircraft, piloted by Anderson, assessed the situation, heavy mist, Full daylight approaching, alerted defenses, and made the decision to abort the mission and return safely. Probably a wise choice. One other aircraft from this wave was also confirmed shot down during these attempts.
So tallying it all up, the cost of the night.
It was incredibly steep. When the sun fully rose on May 17th, the count was stark. 8 Lancasters failed to return. 53 airmen killed, 3 taken prisoner. 56 casualties from No. 617 Squadron in just one night.
A heavy price. But the immediate results, the reason for that cost, were dramatic, weren't they? What did the reconnaissance flight show the next day?
The photos were stunning. They showed utter devastation below the breached Mohninator dams. Massive walls of water had surged down the valleys.
How much water are we talking about?
Estimates are that something like 87% of the Mohn reservoir's capacity and 75% of the Eater's water volume were released. Hundreds of millions of tons of water.
And the downstream damage?
Catastrophic. The floodwaters scoured the valleys for miles. Power stations obliterated, factories flooded or destroyed, crucial road and rail bridges washed away, pumping stations wrecked. It was chaos.
What about the disruption to basic services in the Ruhr industrial area?
Severe. Gas mains were ruptured, electricity generation knocked out over a wide area, clean water supplies heavily contaminated or cut off entirely. It caused immediate and widespread disruption to industry and daily life.
And the human cost of the flooding itself?
Also devastating. The official toll was around 4,341 people killed by the floodwaters. Tragically, the majority of those victims were foreign forced laborers, Soviet prisoners of war, mainly housed in camps situated vulnerably close to the rivers downstream from the dams. They had little or no warning.
A grim consequence. How did the German leadership react to this? This was a major blow.
The reaction was immediate and decisive, which actually tells you how seriously they took it. Albert Speer, Hitler's Minister for Armaments and Munitions, flew to the scene almost immediately to assess the damage himself.
And the response?
Hitler authorized a massive top-priority effort to repair the dams and clean up the damage. Speed was paramount.
How massive are we talking? Manpower.
Speer initially pulled 7,000 workers from other projects to start emergency repairs. But that wasn't enough. This was quickly supplemented by an additional 20,000 workers.
27,000 workers just for the dam repairs? Where did they get them from?
And this is strategically significant. A large number of these workers, particularly skilled construction crews and engineers from the Todt organization, were diverted directly from building the Atlantic Wall.
The coastal defenses meant to stop the Allied invasion.
The very same. Diverting tens of thousands of workers from that high-priority project to fix the dams shows just how critical the Germans considered the Ruhr water supply and infrastructure to be. They also massively beefed up defenses, installing heavy flak guns at all the remaining Ruhr dams and deploying troops, equivalent to almost a full division, just for dam security.
That diversion of resources, especially from the Atlantic Wall, leads us right into the big historical debate, doesn't it? Was Operation Chastise actually worth the cost? We should look at both sides fairly.
Absolutely. The skeptical view has strong points. Firstly, the cost was undeniably high. 8 specialist aircraft, 56 highly trained aircrew lost in one night. That's a heavy price.
And the damage wasn't permanent.
No. The Germans, through that massive effort, managed to patch the breaches in both the Möhne and Eder dams by October 1943. Just 5 months later, they were essentially repaired, although perhaps not fully restored to pre-raid strength immediately.
And the impact on German war production, did it cripple the Ruhr?
This is where the skeptics really focus. One major post-war analysis, often cited, estimated that the overall loss to German armament output in the second half of 1943, directly attributable to the dam raids, was perhaps as low as 5%.
Only 5%? After all that destruction?
That's the figure often used. So, the argument goes, huge cost in lives and machines for a relatively small, temporary dip in industrial output. Was it worth it from that perspective?
Okay, that's the skeptical case. What's the counter-argument? The positive view.
The positive view shifts the focus away from just the immediate, measurable loss of factory output. It argues the real strategic benefit wasn't the 5% dip, but the massive diversion of German resources.
Those 27,000 workers pulled off the Atlantic Wall and other projects.
Exactly. Plus the vast amounts of concrete, steel, fuel, transport, and engineering effort that had to be poured into the repairs for 5 solid months. That's manpower and material that couldn't be used elsewhere, reinforcing coastal defenses before G-Day, building U-boat pens, producing tanks or aircraft.
So the argument is that the raid caused a significant strategic inconvenience and resource drain at a critical time.
Precisely. The positive view argues that this forced commitment of resources, the disruption, the delay to other projects like the Atlantic Wall, and maybe even the psychological blow to the Germans, provided a strategic benefit that outweighed the direct short-term impact on armament production figures. It's about the opportunity cost for the Germans.
It's a fascinating debate. Tactical damage versus strategic diversion.
It really is. And there's probably truth on both sides. But regardless of where you land on that effectiveness debate, the raid's technological legacy is undeniable.
How so?
Operation Chastise stands as this incredible example of wartime innovation. It proved the concept of precision, low-level attack using highly modified aircraft, and completely novel ordnance. Barnes Wallis's bouncing bomb was a work of genius, however specific its application.
And it paved the way for other things.
Definitely. The RAF, and 617 Squadron in particular, built on the experience. They proved the Lancaster could be adapted for these kinds of specialized strikes. This led directly to the development of even larger bunker-busting bombs, like the Tallboy and Grand Slam, also designed by Wallis.
Which were used later in the war.
Famously used by 617 Squadron against hardened targets like V-weapon launch sites, U-boat pens, and perhaps most famously, in the final destruction of the German battleship Tirpitz in its Norwegian fjord. The Dambusters raid was, in many ways, the precursor to those later precision strikes.
So it was a technological and tactical stepping stone, even if the immediate strategic impact on the dams is debated.
I think that's fair to say. A landmark achievement in air power history.
Which brings us to our final thought for you, the listener, as we wrap up this deep dive. We've explored the incredible mix of ingenuity, Wallace's physics, and sheer human bravery, Gibson's crews flying at 60 feet.
Yeah, we've covered the technological marvel of the upkeep bomb, the pinpoint accuracy required, and the undeniable, staggering physical destruction caused by the breaches at Modena Ader. You see the photos, you read the accounts, it's immense.
But that ultimate question of strategic victory really seems to hang on that diversion of resources, doesn't it? Not just the flood damage itself, but the reaction it forced from the German war machine.
Exactly. If pulling 27,000 workers and tons of concrete away from the Atlantic Wall for 5 or 6 months significantly delayed or weakened those coastal defenses ahead of D-Day.
Does that strategic impact perhaps outweigh the fact that Ruhr armament production only dipped by 5% temporarily? Does the 6 months of strategic inconvenience and resource drain matter more in the long run?
That's the calculation you have to make. You have to weigh the heavy price paid by Northern 617 Squadron, those 8 aircraft, those 56 men, against the potential delay and weakening of Germany's defenses elsewhere. Was it a costly tactical gamble that paid off strategically, or was it primarily a stunning technological feat with a more limited, short-term military impact?
A complex legacy, and one we'll leave you to ponder. Was the resource drain worth the high cost? You decide.
A tough question indeed.
That's it for this deep dive into Operation Chastise. Thanks for joining us. We'll see you next time on The Deep Dive.